Welcome everyone to the next seminar. I'm delighted to introduce Vanessa Zema, who's coming to us from the Max Planck Institute in Munich. So Vanessa is an experimentalist working on CREST and the cosinus experiment. But today she will be telling us in more general about this very interesting technology that she works on, specifically centered around the idea of electron scattering. So thank you very much for waking up early to give us this seminar from across the world, and I will leave it in your hands. Thanks.
Thanks a lot, Sharon. Thanks a lot for the invitation again. It's really a pleasure. I will be talking about electroscattering and cryogenic scintillating calorimeters, and focus during this seminar a lot about dark matter. I will also, since my colleagues say that I work in the transition between experiments and theory, the seminar will be a mix of both. Yes, now it goes. Since I will be talking about dark matter, I just want to remark that it's quite impressive that at all cosmological eras, we have evidences that are compatible with the hypothesis of dark matter. So the hypothesis that we have some matter that is not baryonic, so we need some additional matter content to explain the evidences at all times. And these, as you know, are all gravitational evidences. There are two approaches to solve what we call dark matter problem. So add dark matter or modify general relativity. And among the two, today we'll talk about the possibility of adding dark matter. Here I say we do it because we learn from experience. So we know that the standard model was built some now decades ago, and that has been built also in the last time with more particles. So we know that also the standard model is not complete. This comes from the neutrino mass. So makes sense to think about another component of matter. And in particular, you can still break down this in two possibilities, so that dark matter is made of particles or of macroscopic objects or primordial black holes. Now, we know that these two either cannot make the full dark matter content, or if they can, is in a let's say, small window of masses in the case of primordial black holes. So in all scenarios, it's plausible to search for a component of dark matter that is made of particles. And I will focus on this in the seminar. So we don't know a lot about dark matter, but a few things, yes. So we know that it has to be non-baryonic, stable, massive, that has to have couplings with electromagnetism that are weaker than the ones that are accessible with experiments, and the couplings to the standard model that don't, let's say, mess up what we know about the standard model. So they have to be accountable within the experimental uncertainties, and also have to have a cosmological production that is in agreement with observations. Among all techniques that can be used to search for dark matter, I will focus today on the direct detection, and therefore on the technique that searches for scatterings directly inside the target material. And I will start to talk about the observables, and as you see here, I will be talking about direct detection of dark matter and neutrinos, because it's quite interesting that indeed you can talk about them really in parallel. So I divide here the interactions, starting from all the interactions that have as a primary scattering, nuclear scattering. And then I divide the interactions in standard and the ones that instead are effective, so are described in effect field theories. And yeah, so then in the case of dark matter scattering of nuclei, the standard interactions are what we call spin-independent and spin-dependent standard interactions. And in the framework then of non-relativistic EFT, you can extend these interactions to the most general package of non-relativistic interactions you can think about. And this has been done in the literature since now many years. And at the same time, for neutrinos, you can also think about standard interactions and then think about non-standard interactions in the framework of relativistic EFT. So this is the difference between dark matter and neutrinos. Neutrinos are relativistic, dark matter is considered not relativistic. So this is the difference among the two. And then you can add some other standard interactions as has been done also in the literature. So the fact that when you hit a nucleus, then you can also excite some gammas because of the inelastic scattering of dark matter of nuclei. And this has also been treated for dark matter in the literature. I found something also for neutrinos, but not in terms of direct detection. So I put in blue what I think it can be still extended more in the framework of the direct detection. And then it has been also considered something else. So the possibility that when you hit a nucleus, then you also get atomic excitations like due to the Migdal effect or the Bremsstrahlung. And this has been developed both for the standard interactions, but also in the framework of the non-relativistic EFTs. And in the case of neutrinos, I haven't found this for the non-standard interactions. And I think it's interesting. I cannot say right now if there is a reason for that, or it's just that we need to complete the literature about that. Then you can talk about the possibility that neutrinos and dark matter interact primarily with electrons. And in this case, we have to divide the treatment considering that the systems we are working with are different. So in the case of TPCs, for example, where we use noble gas, then we can, it's considered a good approximation to consider isolated atoms. And this has been treated in the literature for all cases that I show here for both standard interactions and effect field theories. But then there is also another topic that is like searching for interactions with electrons in crystals. And while for dark matter, this has been developed and in literature, you can find a lot of work and studies about this. For the case of neutrinos, to my knowledge, is missing, and the treatment has to be adapted. We cannot just use what was developed for dark matter because, again, neutrinos are relativistic. Therefore, we need to develop the theory for neutrinos, a dedicated one. This is now an overview on the observables, and now I will talk about the experiments. And in general, you know that the experiments searching for dark matter are classified by using the type of observable. So we know that we can use phonons, light, and charge. And in the intersection of these, there are experiments that have two channels. And so they can use both, and usually this is used to discriminate the type of particle that is involved in the interaction. I will focus on the intersection between phonon and light, so about experiments that are searching for phonons and the scintillation. And before that, I just show the limits. This plot is well known. So it's in the standard scenario, the cross-section versus the WIMP mass. And we know that in general, you can choose your approach. If you want to probe lower and lower cross-sections, you can use experiments that have large exposures like TPCs. And if you want to go to lower lower thresholds, so probe lower and lower dark matter masses, you can instead use cryogenic detectors, or now recently also use effects like the middle effect that we mentioned before, that allows also to TPCs to probe a lower region of the lower dark matter mass and the parameter space associated to it. And then this, for the case of dark matter interacting with electrons, I took this from a recent paper by Charan and collaborators. And here you see the overview of the experiments searching for dark matter scattering of electrons. And you see here xenon, dark psi, panda X, Damic, Sensei, Edelweiss, CDMS. So they are all now providing limits on the cross section, and here what we call standard, at least I call now standard interactions, are the heavy mediator case and the light mediator case, because these are the two cases that are now shown by the experiments to then share their results. And in this case, for example, for semiconductors, to probe lower and lower dark matter masses, what one can do is to choose materials that have lower and lower band gaps in the electronic bands. I will go back to this in a few slides. So now I will focus on the cryogenic scintillating calorimeters with transition edge sensors. And I want to explain the working principle. So in general, these CSCs are made of two channels, as I said. There is an absorber and a light detector, both equipped with transition edge sensors. So they both work as detectors. And the point is that when a particle interacts in the absorber, then lattice vibrations are produced that fill up the absorber, then they reach the surface, and there they can transmit the signal to a sensor that is placed on the surface of the absorber. And here the sensor heats up and then cools down through a link to the thermal bath. And so when I say thermal bath, what I mean is that there is a sensor, then there is a metal wire that connects the sensor to the copper holder in our case, and therefore this is the bath. So the copper holder is the low temperature. I didn't say what's the temperature of operation. We use these detectors at millikelvin, and yeah, this is because the sensor we are using is superconducting at 15 millikelvin. So yeah, what we see then are tiny increase in temperature in the sensor as a function of time, and this is the pulse that we see in the phonon channel. This is what we call the phonon channel. Yeah, so then when you choose as absorber a scintillator, part of the energy is converted into scintillation light. And then you can choose as a material for the light detector a crystal that is opaque to the scintillation light of the scintillator you chose. And in this case, then the scintillation light is absorbed by the crystal that encapsulates the absorber. And in this crystal, then the photons are converted into phonons that then propagate and again heats up the sensor that is placed on the surface that warms up and cools down through the link to the thermal bath. And this is then the pulse that we see in the light detector. So it's again measured as an increase in temperature versus time. Now, the measurement in coincidence of light and phonons allows us to then discriminate the type of particle that is involved in the interaction, because it's known that for the same deposited energy, an electron recoil emits more light than a nuclear recoil, and this has to do with the mass of heavier and heavier particle or let's say systems correspond to a lower emission in the light. So from the ratio of the two energy depositions that roughly we can say is the pulse height of the pulse, this then is more let's say complex in the analysis, but is a good approximation to consider the pulse height. This is what we do to do the first estimation of the energy. We use the pulse heights. Then, yeah, using this, you can discriminate then the particles. And to show this, I show this plot that is from a paper by Cousinus. And on the left, you see the light yield versus energy deposited in the absorber. And the light yield is the ratio between the energy in the phonon channel and the energy, the energy in the light channel versus the energy in the phonon channel. And on the x-axis, you have the total energy deposited in the absorber. And on the left, you see background only data, and on the right instead data taken during a calibration with the neutron source. And you see that these bands here that are the nuclear bands gets populated because of the neutron calibration. And also what is interesting is this line here that shows the inelastic scattering. So I mentioned before that when you hit the nucleus, then it can happen that you also excite a nuclear state, and then this de-excites and emits a photon. And in the case of iodine, this line is at about 57 kiloelectron volts, and this is what you see in this band here. So it's an interesting technology because you can study different processes and also, yeah, discriminate between electron gamma events and nuclear recoils. Sorry. Yes, so then, some words about the sensor. So we use as sensors, sorry, I have to break. I'm going, like, if you have questions, always interrupt me if, there is something unclear or if you have curiosities. No, so, yeah, okay. So, about the transition edge sensor, this technology has been developed at Max Planck Institute for very long by the CREST experiment, and it consists in a superconducting thin film made from tungsten and some what we call phonon collectors that are made from aluminum. And the reason is that we want to lower as much as possible the heat capacity of the sensor, but at the same time have a large probability of collection of the phonons. So you want to have a large interface area between the sensor and the absorber. And to do that, you use a superconductor, aluminum, that has a higher critical temperature that is around 1 Kelvin. So at the temperature of operation that is about 15 millikelvin, the aluminum is completely superconducting, and its capacity becomes very low, so you can make it larger without affecting the performance of the detector. And the tungsten instead is operated in the transition between the superconducting and the normal conducting phase in a linear region where to tiny increase in temperature correspond large jumps in the resistance that then are amplified using a squid, an electric circuit, the squid, and in the end, what we see the observable is the pulse I mentioned before. What is also interesting is that these detectors have been described theoretically in detail already in the 1995 with a system of differential equation that couple the change of temperature with time with the thermal conductances and the power input injected in the sensor and in the absorber. And these equations can be solved analytically exactly, and then you obtain a function function for the temperature in the TS that then is empirically described as the sum of non-thermal component, we call it, and thermal component. That means there is a part that describes the effect of collection of the non-thermal phonons, and the other part instead describes the thermal phonons, so the contribution to the pulse shape due to the thermal phonons. Yeah, I underline this because we do studies about these conductances, and it's an interesting topic, again, in between theory and experiments. So now I want to focus on the existing cryogenic scintillating calorimeters, and stress that they are used for dark matter nucleus scatterings and CEvNS. So CUSINUS is using sodium iodine transition edge sensors, CREST, different materials. It is versatile, can use calcium tungsten, sapphire, silicon, and others, as all equipped with the transition edge sensors. And the nucleus is using calcium tungsten and sapphire equipped with transition edge sensors to search for CEvNS. So the reason why CUSINUS is using sodium iodide is that the goal is to cross-check the result by Dama Libra. So it's using the same target material, and is cross-checking the signal in a complete model-independent way in the nuclear recoils. And the absorber is sodium iodide, and the light detector is made from silicon. And to use sodium iodide as a cryogenic detector, CUSINUS had to develop a different design with respect to the one that is usually used for to couple the TS to the absorber that we call REMO TS. And this is due to the fact that sodium iodide is a difficult material, so it's hygroscopic, so you cannot expose it to air, and has also a low melting point. Therefore, you cannot produce a tungsten film on the surface. And now instead, what is coupled to the surface is a gold pad that is then connected to the TS through a gold wire, and the TS is then fabricated on a remote crystal, so on a different crystal. So here I show just some pictures of the facility and of the collaboration and of the detector design. Then CREST is searching for dark matter nucleus interactions, and as I said, has a versatile choice of target materials. At the moment, is working to mitigate the low energy excess. That is this observation of events at low energies that are a background, that at least the hypothesis that there is a signal there is disfavored, and it cannot be a measure component. And the observation is that below about 200 electron volts, there is a rise of events. And a lot of work has been done now to understand this background. There is a workshop that is dedicated to it that is called the Excess Workshop. What I want to stress here is that recently CREST has shown that they reached sensitivity to single photons in the light detector. And I stress this in particular not only because it's interesting, but also because it's important for this seminar. And then Nucleus, as I said, is searching for CEvNS, is developing cryogenic scintillating calorimeters that then will be exposed to the flux from a reactor. And the goal is then to search for the coherent scattering of neutrinos, of nuclei. Also them working hard to reduce the low energy excess. Now, the gap. So existing CSCs for dark matter and neutrinos are used for nuclear recoils, and there are now ideas to search for also electron recoils. In particular, there are two projects, Daredevil and Tesseract, both Daredevil is using gallium arsenide equipped with a neutron transmutation doped at the moment, so a different sensor, but the plan is to use transition edge sensors in the future. And Tesseract is like they have a different diverse program among in this program. There is also the idea of developing gallium arsenide CSCs and then measure electron recoils using transition edge sensors as well. Now I will focus on another idea that is to use sodium iodide cryogenic scintillating calorimeters to search for dark matter and neutrino electron scattering. And first of all, I want to spend some time to explain the working principle. So in general, when dark matter interacts or dark matter, or let's say a particle interacts with the system that has an energy gap, then an electron is excited from the valence band to the conduction band, and in the de-excitation then can release the energy that then we measure. And for this, since it's an elastic scattering from the conservation of energy, you get a relation between the deposited energy, the transfer momentum, the velocity of the incoming particle, and also the dark matter mass. And here, this theta is the angle between the transfer momentum and the incoming dark matter, the incoming particle, dark matter in our case. So the transfer momentum, since we cannot measure it, we can assume that is multiples of, we can consider multiples of alpha ME, where alpha is the fine structure constant and ME is the mass of the electron, and this I is just the multiplicity that I use here in this graph, where I show the maximal transferred energy versus the dark matter mass. And the point is that even using the lightest nuclei, if you want to probe lower and lower dark matter masses, searching for dark matter scattering of electrons is kinematically convenient. So this is the reason why we are interested into this, is to probe a different region of the parameters than the one that you probe with nuclear recoils. And in general, you imagine that for searching for dark matter interacting with electrons, you want to use semiconductors. And the reason is that semiconductors have very small band gaps that then are convenient, as I mentioned before, to probe lower dark matter masses. But indeed, scintillators also have a band gap. In the case of sodium iodide, is found between 4 and 6 electron volts. And you can use also this to search for dark matter scattering of electrons. And indeed, now I will focus on this idea. And I show here the spectrum that you would observe in the absorber using sodium iodide. And I show this for different models, again, heavy and light mediators. And to do this, to obtain this plot, we use QAdark, that is an open source code that is available since now many years, and allows to calculate the differential rate in crystals because it also tabulates the form factors for different materials, and among those also the one of sodium iodide. So this plot was obtained using this formula here, where this is the form factor of dark matter that has this shape, and then in the two cases it gets the different dependence on the Q squared. So now this is the spectrum you observe in the absorber. But what we know is that in a scintillator, the energy deposited in the absorber is can also be converted into photons. And in particular, in the case of electron scattering, one can calculate the number of photons that are emitted by using this formula here, where EE is the energy of the electron, EG is the gap of the scintillator you're using, and this PEG is, in particular, P is a parameter that is material dependent and parameterizes the amount of energy that you have to deposit to then produce two or more electron hole pairs. That is not just the gap, because part of the energy is lost in other channels, or let's say is converted into other channels than scintillation. And here, by using the assumption that the gap in sodium iodide is 5.9 electron volts, and that this term here is equal to 3, this is like using literature, we assume the same, we use the same assumptions. What you get is that the energy the energy threshold to produce 1 gamma is the gap, and you produce 1 photon until 23.6 electron volts. And this is the threshold to then produce 2 photons, and you will produce 2 until 41.3 electron volts. And now I want to focus on what you see in the light detector. And there you see peaks that are centered at multiples of the energy gap, because we are using as light detectors calorimeters. So you measure all the energy that is deposited in the light detector. Therefore, in the case of 1 photon will be the energy gap. In the case of 2 photons will be twice the energy gap. Now, in this plot, I show also a broadening of the peak that we assume Gaussian and comes from the resolution of the light detector. And I remind here that 1 electron volt is the resolution of the light detector that was achieved by CREST and shown recently. So it's a reasonable resolution. So this idea that I've been discussed so far is not a new idea. So the idea of using scintillators to search for dark matter electron scattering was already proposed in 2017. And then the idea was to use an array of transition edge sensors placed on the surface of the absorber. And like at that point, the idea of using a separated light detector was not considered, because the sensitivity of the light detectors were not yet enough to then detect single photons. But now that CREST showed that this is feasible, then this becomes a possibility, and this is what we are now considering in this work. So here I show what then you expect to see if you also consider that you have a background in the light detector. And since the light detector is a calorimeter, you expect to have to observe also the low energy excess. And in this graph, I show the low energy excess that was detected in a silicon wafer by CREST, is published in this paper here. And this line marks the threshold of this detector. And here there is an extrapolation of the spectrum that was shown there. And I remarked that to visualize the peaks, I had to suppress the background by a factor 10 to the minus 7. So this means that the low energy excess is a severe limitation for this search. So this stress even more that we need to mitigate this background to do then interesting research in the case of dark matter electron scattering. But being optimistic, thinking that now we detect a signal, we also like studied how would you determine the mass, the model that is producing the signal that you see, considering that there is a degeneracy between the transfer momentum, the dark matter mass, and what's the observable that you can use to establish which dark matter mass or which model of dark matter produce the signal. And in this plot is shown that you can use the number of peaks that you detect in the light detector for that. Because, for example, if you use if you consider that we observe 5 peaks in the light detector, then in this graph you see that this marks the region where the dark matter mass is larger than 40 mega electron volts. You see here that this goes down to larger dark matter masses, and a transfer momentum that is larger than about 8 alpha ME. So the observable that we can use to understand which dark matter mass produce the signal is the number of peaks. Now, after discussing this idea, we also thought, okay, what's the optimal detector design that we can use to do this search, and what are the open questions? And to do that, we wanted to answer the question, do we need the phonon channel? Because so far I've been talking about the light channel and didn't consider what's the additional information that the phonon channel could give. And here we show on the y left axis the number of peaks, on the x axis the dark matter mass, and on the right y axis the energy in the phonon channel. To calculate this energy in the phonon channel, we do the easy assumption that all the energy that doesn't go into the light channel goes instead in the phonon channel. And the solid lines here show indeed the energy in the phonon channel. And if we take the same example than the one taken before, so that we observe 5 peaks in the light detector, in the phonon channel, you would need to scan through this curve to then provide an information on the dark matter mass. So not to give just a range, but to give a measurement of the dark matter mass that produce the signal. And to do that, you would need a very good resolution in the phonon channel. Here you see that it's a scan of about 10 electron volts. And to do that, then you would need a tiny absorber, because in cryogenics, the resolution, so the performance of the detector, improves if you lower the mass of the absorber. Then you can use other methods to improve the sensitivity, but this is an easy relation that really shows that if you make the crystals smaller and smaller, then you are more and more sensitive. So the conclusion of this plot was that for signal detection, we don't need the phonon channel, while for selecting the model, yes. Now, considering this idea, then we sketched an idea on the detector design, and the idea would be that we could make this compromise of not using the phonon channel, and then make the absorber bigger, and we could then enclose the absorber in an array of light detectors, so that we don't use a single mass that would then again reduce your sensitivity. Instead, we use a lot of wafers that have a very good resolution, and then they would be sensitive to single photons. And then what you have to do is to cover the absorber completely to enhance the detection efficiency, because we want to measure single photons, so we cannot afford to lose them because of some line of sight. And indeed, one of the idea would be also to put a reflective foil around so that we can collect the ones that escaped. Another point that we discussed was, okay, how do we measure the electronic energy gap at millikelvin? Because this was not done. It was done at Kelvin, but not at millikelvin. And anyways, it's always like a good approach to measure the material properties of your own crystal. And to do that, we thought that we could use an iron source fixed to a screw to collimate the source on the surface of the crystal. And then in this way, we would intensify the number of photons that are emitted. But then, since we want to measure the single photons, we could reduce the size of this sensor here that we could use then as a light detector, but single photon detector. And in this way, we could reduce instead the number of photons that we detect so that we would see single peaks. And from the difference between two peaks, we could then give a measure of the energy gap. So we would basically use the solid angle so that we don't get the large number of photons emitted after the interaction of the X-rays from iron that are about 6 kilo electron volts. And if you consider that the light yield of sodium iodide is about 10%, then it would be 600 electron volts. And if 1 gamma is about between 4 and 6, you understand that is a lot of photons. So we want single photons, and therefore we would use the solid angle to reduce the number. So on top of this, that would be the idea to search for, to measure the band gap. There are other parameters that we need to study. So in particular, we need to study the scintillation at low energy and low temperature. And scintillation is a complex solid state mechanism. What I didn't say is that in the case of sodium iodide, the scintillation is induced by the formation of self-trapped excitons are called. An exciton is a bound state of an electron hole pair. And self-trapped means that there is a deformation of the lattice around this exciton. And this is the state that then generates by the excitation, the production of light, and is a complex mechanism that at low energies has not been yet studied at millikelvin. So we want to then do more measurements and characterize the detector for this search. Then using assumptions, because we haven't done yet the optimization of the detector, we drove some projections to understand if this project is interesting or can give some new information. And what we got is that by using 1 kilogram year of exposure. So we could use, for example, 500 grams of sodium iodide or 1 kilo of sodium iodide exposed for 1 year. Then you would you could get these projections using pure sodium iodide, and the projections are obtained with an energy gap of 5.9 electron volts and the light detector energy threshold of 1 electron volt. So we are considering a better light detector than the one that is currently available. And then you see that for different suppression of the low energy excess, you would get different curves. Here we put 10 to the minus 4 and 10 to the minus 8. And for different efficiencies. So where efficiency in this case is including both the light yield of the crystal and the detection efficiency. And here we consider 0.1 to 1 because, as I said, it was shown in a sodium iodide cryogenic calorimeter that the light yield that the light yield was 13%. So we consider the good hypothesis 0.1. And here I showed for light heavy mediator and light mediators. So the next steps to extend this work are to draw projections not only for these standard scenarios, so light and heavy mediators, but also to a more general set of interactions. And for doing that, you need to calculate the atomic wave functions in sodium iodide, also to include the medium effects that has been shown to be, to play a role in the level of event rate that you expect. And by studying this, starting in particular in this first point to extend the work to different types of interactions, we started to think about neutrinos as well and the possibility of detecting them because there are scenarios in which dark matter and neutrinos have similar couplings. So, for example, in the case of electromagnetic couplings, like the magnetic dipole or anapole. And since this has been also discussed for neutrinos, we started to also think about this phenomenology. And to start to think about that, what we did was to use the simplest kinematics, so elastic scattering of neutrinos of electrons. And from the quadri-momentum conservation, you get that this is the maximum energy of the electron recoil. And considering that our detectors are sensitive into the electron volt to kilo electron volt energy range, we realized that by using solar neutrinos, we could obtain an energy of the electronic recoil that is visible. And indeed, this energy region here corresponds to this high flux here of the solar neutrinos. That then is shown here more closely. And you see that PP, the PP chain, has a flux that is very high and the energy range that we are interested in. So we will focus on the PP flux for, let's say, in the next slides. And I wanted also to remark that now using CEvNS, Xenon and TON and Panda X recently shared the great news that they measured the boron 8. This is a very exciting now new frontier for the direct detection. Now, as I said before, there are different types of interactions that you can consider for the case of neutrinos. The rate is similar to is a differential rate. So you have a number of targets, a flux that is in our case the solar flux, the probability of oscillation, and the cross section. Where here I put a question mark because you can add some non-standard interactions, and for Dirac neutrinos you can consider a dipole magnetic moment, and for a Majorana neutrino here we consider the nanopole magnetic moment. And by plugging this into the differential rate, you obtain that for the case of the magnetic dipole, at low energies, you get the enhancement of the differential rate. And this is an effect of the cross-section. It was very interesting for us to also observe that the best limit on the neutrino magnetic dipole was achieved by Xenon and TON. You see, this is the current limit. So the point would be that here you see that I'm considering a TON here. So of course now is something like projected into the future, because you would need an array of cryogenic detectors to do this kind of measurement. We are studying the phenomenology to understand if these detectors can give an information, and already seeing this enhancement. This is calculated using this limit, so the experimental limit on the magnetic dipole. The anapole is basically negligible, so it will not give any effect with respect to the cross-section of the standard model. And this is also interesting because, again, the dipole moment only Dirac neutrinos can have. Like if one wants to dream and you say, okay, we measure a flux of neutrinos thanks to this enhancement, for example, then you could give information on the fundamental properties of neutrinos. So I want to also stress that here no detector effects are considered. Also, we know that it's not elastic, the scattering, but inelastic. And also that here no screening effects are considered. So we are now working on this phenomenology. So I cannot see the time right now. I hope I was not too long. I have a short summary. It's just to say that we can probe physics beyond the standard model by searching for dark matter and detecting neutrinos. We have to consider all the possible excitations that can be induced by primary interactions with nuclei and electrons, and also by neutrinos and dark matter eventually. So the CSCs are very sensitive detectors that are probing now nuclear scatterings, but so far they have been used for nuclear and electron scattering that have been used so far to search for nuclear scattering. And here we are now talking about the possibility to search for electron scattering as well. And other thoughts, these are just thoughts, it would be very interesting to build detectors that can detect neutrinos, because to detect solar neutrinos, the performance and the exposure is demanding. So in the meantime, we could search for dark matter with these detectors and then use neutrinos to see a signal and then calibrate and understanding the observables of our detectors. And also I want to say, who knows if the neutrino and dark matter sectors are connected. We know that neutrino have mass, and this is a proof of physics beyond the standard model. So it's an interesting topic to say, okay, we could extend the standard model by studying neutrinos, and this could give information on the dark matter sector. Who knows? This is, just thoughts. I will then, conclude here. I thank you for the attention.
Thank you very much. Do we have questions for Vanessa? Please just go ahead if you do. Otherwise, I will start. Maybe I'll start with the most recent thing you talked about, which is the neutrino electron scattering. It looked like from the formula you were using, you were assuming neutrino scattering off of basically 3 electrons. Is that an acceptable approximation for these energies that you're considering? Because there will be some
for the neutrino.
Because there will be like atomic effects and also the medium effects for this. Did you consider those yet? Or?
It's not a good approximation, no. Mm-hmm. It's just that this was developed now as a follow-up of the dark matter electron scattering. It was the topic of a bachelor thesis. So we started from the basics just to have an idea of what you would expect. Mm-hmm. And now this is what we want to do next. So there is this a very useful tool is called SNUDD, is solar neutrino direct detection. States for this is an open source code that one of our students, Pablo, is started to use, and the goal is to extend these calculations for sodium iodide and consider inelastic scattering, binding energies. It's not like we know that there are bonding energies, and we know the bonding energies, so one can plug them in and already see what's the effect of those. And this is straightforward. Then less straightforward is to consider the crystal effects. So let's say if we are in the approximation of isolated atoms, the next step is easy. For crystals, it's less easy because you have to calculate functions and then use the relativistic case, and then it will be less straightforward.
So the other thing I wanted to ask, so regarding the sensitivity plots for the dark matter electron scattering, so you showed a few possibilities. So I'm sort of curious initially as sort of what you think is the most realistic of these lines, because of course you have this sort of quite tough competition from both xenon, which is very large, and also the CCD experiments where the silicon will beat you in terms of the band gap. So it's I guess you're sort of in the middle. So like you need to optimize and reduce backgrounds to a certain level so that you can sort of carve out your position there. So I'm just curious sort of what you think is a reasonable level of background reduction and efficiency.
So efficiency, I think that we can improve the one we had before by using this new design that we haven't used before, that maximizes even more the collection efficiency. And the open question is the scintillate, like this assumption is taken by considering the scintillation at higher energies. So to know then the light yield. So we can do our best to improve the light collection, but then what's the light yield? We cannot say. We need to measure it. And yeah, this could be then counterbalancing the larger collection efficiency. For what concerns the background, this is, I think, the limitation at the moment. So I cannot say what's the realistic scenario between 10 to the minus 4 or 10 to the minus 8. I think they are both same. They have the same probability at the moment. I could say maybe 10 to the minus 1 is more probable than 10 to the minus 4 or 10 to the minus 8. But the two here are equally probable. And the point is that this is my own point of view. So we don't have surface rejection. So we cannot reject events that come from backgrounds that come from the surface, at least not yet. One idea that I think would be useful would be to match the materials of the sensor and the absorber that you're using, so that you reduce the stress on the surface due to the thermal contraction. And this is something we have been discussing also during the XS workshop. And the effect that you would get, I don't know yet, but there is this idea that I have since some time that after we try this, then I can answer this question better. So at the moment, these scenarios today are not yet. I cannot give an answer on this, unfortunately.
And so why did you assume the sodium iodide for this particular example? Is that just basically what you're sort of planning to use or are using with cosinus, or because you could also have the gallium arsenide or calcium tungstate or sapphire. I don't know band gaps off the top of my head, so I don't know where these end up. But do any of them do better than sodium iodide? Is sodium iodide kind of the obvious choice for dark matter electron scattering out of the materials that you're interested in?
No, not better than gallium arsenide. Actually, gallium arsenide has a lower band gap. Indeed, that's been considered. The choice of sodium iodide with respect to calcium tungstate or sapphire is the light yield. It's a very good scintillator. If it is pure at low temperature, this is a very good light yield. The difference is at room temperature that you need to dope. But yeah, at low temperature, no.
Mhm.
It is also interesting because you see that the temperature is making this difference because you have these self-trapped excitants. And yeah, the other reason with respect to gallium arsenide at the moment is that we know sodium iodide well after years of development, and we have already the contact with the company that produces the sodium the crystals that are pure and have good properties. So is this the reason, like in the comparison with gallium arsenide? Also, there are already projects with gallium arsenide, so it's always good to have a different material and then compare. Also for the calculations, for example, if you do condensed matter calculations to understand better this mechanism, that is something that like I work also with. Now with other people to work on to develop this. So I'm working with Riccardo Catena, Nora Taushofer, and Nicolas Spaldin to calculate this condensed matter properties for sodium iodide. And it's always good to have then to do it for both and then compare. So it's an opportunity that you can get out of other developments.
I also wanted to ask a bit about this, the background and this low energy excess, because I guess you're assuming here that you basically just have an overall suppression of that low energy excess by some amount. But
Yeah.
I don't know currently what the status of the understanding of this excess is, but one of the things I heard was that it was to do with, crystal relaxation or stresses in the crystal, which were just sort of creating events. So I'm just wondering, like, how do you reduce a background like that? And is it as simple as like a reduction strategy would just lower it, or would it change the spectral shape of it as well in some sort of strange way? I guess I don't really know fully the status of this excess, but how do you reduce a background like that, I guess, is the main question.
Yeah, like my approach would be the first thing I would try is this matching between the sensor and the absorber materials in terms of thermal expansion coefficients, because if you think that you cool materials very fast and they just contract differently at different times in different moments, you can imagine that there is like that you induce a stress on the surface. And this would be a first try to minimize this contraction that you know that is there because you're lowering the temperature. And other ideas that have been shown already have different groups have been working on this already is to use two transition edge sensors. It's called like double TS to then see the coincidences and reject single events that you see only in one TS, so that you can reject these events that are in the TS or closer to it. So this is an attempt that is going on, let's say at the moment, and we need to wait for the results of this. And the bulk, like anything that is related to external radiation has been rejected as a measure component because it doesn't scale with the mass. So this you cannot consider so dark matter as well, right? So and the idea that now, since there is not yet surface events rejection, for me points towards this, like that we really need to work on those events there, because then if you imagine that you have this stress on the surface, it's basically a deformation of the lattice, and then when it relaxes, emits a phonons. That makes sense, let's say. Then you can also work on but this has also been done on the emissions like luminescence. For example, if you use silicon dioxide, there is some luminescence there. So we need to study, I think, these effects.
Yeah. And I guess so the other thing that came to mind, I have no idea how relevant this is, but like in the many years ago, people in the context of like Dharma Libra were speculating on the possibility of channeling. So like some effect to do with the lattice structure and photons being emitted in different directions relative to the lattice structure could lead to some effect. And I think that eventually was sort of discarded as being important in the case of Dharma, but I'm just wondering for these sort of cryogenic scintillators, do these sorts of lattice alignment effects and to do with like light propagation and maybe also the phonons, do they become important? Is this like something that people talk about, or is the sort of shape of the lattice sort of not seem to be important?
People talk about it, directionality using the different axes, but I would not know now. I cannot give you a number like how much effect there is due to that. But yes, it's something people discuss using the anisotropy basically of the crystal to enhance the effect. So yes.
Okay, well, yeah, I mean that was just a sort of curiosity.
Yeah,
Okay,
sure.
well, yeah, okay. So thank you very much. I will